So I was supposed to cover eager evaluation in about 5 minutes and spend the rest of the lecture on lazy evaluation. So we have 5 minutes for lazy evaluation. So what's going to happen is we'll do lazy evaluation, mostly we'll finish. Who knows how long that will take? But I think it'll take shorter because, you know, concurrency is just this new way of thinking. And lazy is, but you know, again, the eager evaluation I've given you, you go and look, at least when I Googled and Andrew Googled, there's no algorithm that we can just find and, you know, port to this thing, to this class. And same thing with these, lazy evaluation is a concept. We can't find an algorithm. And so he and I have been working it out. And hopefully what I present to you will work out correctly. But let's go and at least use the 5 minutes. So what we're going to end up doing is do lazy evaluation next on Tuesday. That leaves us with one class. And I thought we'd have many classes after this stuff. And I'd like to sort of summarize what you guys learned, but I also want to connect all the concepts we've learned to sort of concrete syntax that you see in different languages, because not everything I'm talking about is in Lisp. Okay. One of the things that anybody who's taken programming language should know is call by reference, call by value, and there's something called call by name. Okay. And you will and call by name is something that people don't really understand unless you know lazy evaluation. So that's why I want to do lazy evaluation before that. So that's one thing I do want to do before we leave. Okay. I'd like to show you Curry working in ML, but maybe we'll do it, maybe we won't. Prolog, you know, you can study on your own. You guys are smart enough now after this class. But that's kind of the goal. I want to also do procedure parameters, show you how the various ways in which procedure parameters are done. So, you know, who knows how much time we have. But those are kind of my goals. Okay. And let's just start on lazy evaluation at least. Okay. We can use every second we have. So I talked about regular evaluation, which is and we saw this in the context of the Boolean operations, right? We said we can do the two Boolean operations, do operands of the Boolean evaluation expression one after the other. We can do them in parallel, or we can do them if we really need to. Okay, and if we really need to is sort of, you know, is done by the by this operation. This operation always does it. So essentially, this is the non-lazy version, and this is the lazy version. Okay, the second operand is evaluated only if we need to, otherwise we don't. And that's hardwired to these logical, these Boolean operations. So what we're going to do with lazy evaluation is extend this notion of laziness from lazy Boolean operations to lazy computing, whatever that means. We want to broaden that somehow and go take these small steps further. Okay, and one small step is lazy function calls. So let's go and look at this piece of code and see where laziness could help. So I'm defining print1 arg. It takes 3 parameters, x, y, and z. It checks the value of z. If that's true, it prints x. Otherwise, it prints y. Okay? And I give it the value func call plus 5.3 minus 5.3 greater than 5.3. So how would laziness benefit here? What would it mean to be lazy? Yeah, Chris.
So maybe if it's not doing lazy evaluation, it will automatically calculate y, but like just for the first one, it's 5 is greater than 3, so we will only need to calculate the x.
Okay, so if you get this, you got 50% of what I want to convey in laziness. Okay, so it's checking the value, its third argument. There's a reason why I made it third. We'll see that later. I made it the first argument first. And this happens in any piece of code. That based on certain conditions, certain parts of the code are executed and other parts are not executed. In fact, when people do evaluation of test cases, they want to make sure that your test cases are so complete that every piece of code is covered. The corollary of that is that if there is some input that doesn't exercise all pieces of code, doesn't require all pieces of code to be exercised, don't execute them, right? And that kind of happens, except when we look at these arguments. That our argument evaluation strategy is, before we call the method, before we call print one arg, we go and evaluate all of the arguments. Okay? The halting problem tells us that we cannot look at print one arg and determine exactly what arguments it will go and access. We have to run it to figure out what really happens. So lazy evaluation basically says that we will not evaluate the arguments when they should be evaluated according to the manual, but we'll evaluate them if they're really accessed at runtime. Okay, that's one aspect of going from. So that's what means going from lazy Boolean operation to lazy function calls. Okay, without even looking at the function here, we want to be lazy. Okay, so in this case, as Chris mentioned, there was no need to go and evaluate minus 5, 3, because 5 is greater than 3, so this particular path is taken, and we only print x, so we need to evaluate plus 5, 3. We never needed to evaluate minus 5, 3. Okay, this might have been a very complex operation, but this is just the opposite of eager. Eager said, let's go and evaluate all of them in parallel. Okay, and lazy is that we'll do them on demand. Okay, yeah, Andrew. Okay, so if we were to implement this, okay, let's go and think. How would we implement this?
I mean, I would think that you would pass the S expression to the lambda, and then what we don't actually have, like, we don't do much with like the lambda evaluation. So I guess what would happen was you would.
Okay, let's go and make this. You know, I'm showing you the exact code here. Right? Okay, so we can go and look at the piece of code here. So this is my lambda, okay? And what the lambda evaluator does is it evaluates all of these arguments. These are the actual parameters. It goes and stores their values in the environment with the formal parameters. And you're suggesting, clearly we don't want to do e1.eval, en.eval here, okay? So what we can do instead is what? Just not evaluate it, right? So just remember what the flow of control is. We go and first associate with P1, E1 eval, then with Pn, P2, etc. eval. Then we go and call lambda.eval. Lambda.eval goes and looks up these variables. So it goes and does a lookup on environment for each of those variables and uses those values. That's what we have so far. And if we want lazy evaluation in that argument, what would we do? What you were suggesting was that we go and just store E1 with P1, En with Pn, and so forth, right? That's kind of the most direct thing to do. Then when we go and evaluate this, we'll go and, we'll have to go and change something here then. The lookup just assumes an evaluated argument. Now the lookup gets an unevaluated argument. So what should we do? Evaluate it, okay? So this is what we did. This is where it goes here, and this is where it goes after that. Right? We have 3 minutes. Okay. So this is what I do now. Everybody happy? Nobody should be happy. Okay, I set Q x1. I set Q y2. I call lambda with variables x and y, to which I pass the arguments y and x. When I do the evaluate here, what is going to happen? So x got associated not with the lookup of y, x got associated with the atom y. Y got associated with the atom x. Now I go and do an evaluate, look up look up x, I go and try to evaluate y. I do a lookup y, try to evaluate x. I look up x, I'll try to evaluate y. And what's the fundamental problem here? Sorry? Okay, it's shadowed. The environment in which E1 was supposed to be evaluated is not the same as the environment in which it's actually evaluated. This was E1 was supposed to be evaluated in the parent environment. When you call the lambda, the environment happens to be the child environment pushed on top of the parent environment. So you're evaluating something in the wrong environment. But we know how to solve that problem, right? We know now, so these environments are different, okay? So two environments not the same, caller versus caller environment. So what's the solution then? Sorry? So we have to go and, okay, change the environment. So when we go and associate with P1, we should associate with P1 not only E1 but also the environment. Okay? If you guys got this much, call by name is pretty much this particular thing. So that's what we look at next. And we've got the basic idea of lazy, and I think we will be able to understand and finish lazy on Tuesday. Okay? So we started on lazy evaluation last time, and we saw that, you know, we wanted to go beyond just Boolean operator lazy evaluation. And the example I showed you was a function that takes 3 arguments, and it evaluates the third argument, and based on its value, it either prints out the first argument or the second argument. Okay? So there's no need to go and evaluate an argument that will not be printed. In this example, there's no need to go and evaluate this particular expression. So we can save computing resources this way. Okay. So we do this. We need to postpone evaluation. So this is what we have. These are the 3 sets of procedures that are relevant to what we need to do. And this is how we did things when we weren't doing lazy evaluation. And let me sort of back up and say that lazy evaluation is a form of optimization. Okay? And optimization says, look, any system that optimizes says, I as a system know better than what the programmer has specified. Okay, so I'm going to go and muck around with what you did so that things are faster. Okay, and there's a well-known saying that if your program is not working, turn off the optimization. Okay, so whenever we try to go and cheat, you know, we were web. Whenever we try to do something tricky, and so be careful. Firstly, everything I'm describing is from first principles. It might have mistakes, and even if it does what it's advertised to do, we may not achieve the same semantics as what we can get with non-lazy evaluation. Okay, so that's sort of a warning. Okay, so this is the gold standard. This is what we want, but this is not necessarily how we want things. So so let's go and see what's going on here. There's the LAMBDA application, and what we want to do is, what normally happens is that in a LAMBDA application, all the actual parameters are evaluated. That's what this is saying here. We evaluate E1 to En, and each of the actual arguments is then associated with the formal argument. Okay, that's what the application does, and then that environment is passed to the lambda itself, which goes and takes whatever environment it has and evaluates its optional expressions and the required expression in that environment. Okay, and when you're evaluating in an environment in which some variable has to be looked up, then we have to figure out what happens when we go and evaluate a variable. And what we did so far is that we just go and look up the value of the variable in the environment. The variable has been associated with an evaluated value, so we get back an evaluated value. Okay? So this is the way things have worked. And the question I posed last time before leaving was, how do we want to cheat here? And Andrew's suggestion was that basically and what we need to do is basically postpone evaluation of these arguments, right? So rather than evaluating it, we could just go and store with P1, Pn the actual expressions that have to be evaluated and evaluate them later. Okay, maybe in here. So that's what we did. So this is how things were, and this is what was Andrew's suggestion, that we go and just store the expressions themselves, not the evaluated versions with the parameters. And when the eval occurs, the eval here results in lookups, and so far our lookups just return the evaluated value stored with the variable. Now the lookups are going to evaluate the argument, and so we only evaluate the ones that are looked up, and we look up only those things that are needed. Okay, so that was a suggestion, and you guys remember, or I don't know whether we got into it, this or not, but what's the drawback of this approach? I think we did get into this last time. Yes, so what we did was, good, nice note taking there. So we go and set q x to 1, set q y to 2, then call a lambda expression where we have y and x being passed, are both the are the actual parameters, the y and x in the outer environment. And there's also x and y in the inner environment in the lambda. And if you're going to evaluate y and x at evaluation at lambda call time, then we cannot access the y and x that were shadowed because they are no longer visible. Okay? So the fundamental problem is that the environments in which the expressions were to be evaluated and the environment in which we're actually evaluating them are different now. Okay? This is what happens when you start cheating. Okay? That you have to worry about things like this. So that's one problem. I think so two environments are the same, caller versus, so callee versus caller environment. Okay, and here's another expression that I believe will cause problems. So right now I'm going to pass to the same, well, not the same. I've got another lambda which takes variables x and y which are not shadowed by which are not shadowing the actual parameters. So there's no shadowing here. But I'm doing set qy to plus xy and then returning y. Okay, why am I doing that? Some of you actually did that in your exams. Okay, but this is a valid Lisp expression, and it's a simple Lisp expression. So there's no shadowing. And I'm going to claim that Andrew's solution again will not quite work. So we're overriding the y, and what's our lookup saying? What's our evaluation of variables saying? That whatever is stored with the variable, evaluate it, right? Now, let's go and look. When we go and first evaluate this x and y, okay, at the plus level, at that point we do want a and b to be evaluated, right? We don't want a and b there. We've got, because we passed E1 and E2, so we do want a and b to be evaluated, the values that are assigned to a and b to be evaluated. Okay? And then what are we doing? We're taking the evaluated value, returned by plus, and storing it in y. So when I go and refer to, so lookup needs evaluation here. Okay? But when I go and refer to this y here, the value is already evaluated, so I shouldn't evaluate again. Now, if that value is an atom, it doesn't make a difference, but we know that when the value is not an atom, two evals is not equal to a single eval. Okay? So there is no distinction between evaluated values and non-evaluated values. Okay, so two problems. First, we can't distinguish between when a variable can be associated with an evaluated value or a non-evaluated value, and we can't distinguish between them. And the second problem is that the environments are different. Okay, everybody buy these two implementations? So non-formal parameters never need evaluation. Okay, we are doing this only for formal parameters. Okay, and even y is a formal parameter here, but we assign to it. It's a very bad idea to do so, but it's allowed. And I've assigned to the formal parameter, and so if I assign to the formal parameter, even for formal parameters, I can't distinguish between the evaluated values and non-evaluated values. Sometimes I need to evaluate them, sometimes I don't. So these two problems suggest a solution, and anybody want to suggest something to overcome these problems?
So I don't think this is probably the right way, but if we encapsulate the parameters we pass in a function, because then the function will have its scoped environment. They'll only access the variables we need.
Okay, so you're trying to solve the two problems. You're trying to distinguish between evaluated and non-evaluated values, and you're saying, look, we've got some, and you're into reusability, but you should be. So we already have functions, so we encapsulate the value in a function, and we know functions have environments in them. So the two things we want is encapsulation, and we want environments to be stored. Okay, so there you seem to be in the right direction. But before you even gave the answer, you said, look, I don't think it'll work. So why didn't you think it would work?
I think this is. I feel like it's like a little. I just feel like there's probably a better way to do it than that.
Okay, better and correct is two different things. So Nathan, you had your hand up.
If you're looking to see if a statement is evaluated or not, you could just use a Boolean variable, or like, for example, in this case, something to
So you need some kind of flag, but you need also an environment.
like a flag, like some kind of Boolean variable.
Okay, and you also need this environment.
But it's probably the most memory intensive way as well, because you can.
Okay, so memory is cheap. Okay, but is this, a function is a very well defined object. Okay, and a function is something that associates a piece of code, a function of definition with an environment. It's not something you evaluate directly. Okay, you evaluate it with an environment and you evaluate it later. So you need actually, so imagine that there was no functions because you're trying to cast your problem, putting a round peg in a square hole. If there were no functions, what would you do? Let's go along with Andrew's suggestion. Because function doesn't quite apply. We are not sending a function. Okay, we've got an S expression. Sorry?
I would still do that. I would still put a Boolean. That's what I would do. So it's like
You would associate.
We already use this concept when using lists, because basically our flag at the end is it nil or not? That's our flag. We actually flag everything we do by putting a nil or not. So you can put something.
Okay, so.
You're asking what I would do.
Okay, so since you're persisting with your solution, which I was hoping you wouldn't, so I have an S expression. I have an X expression. How do I add a Boolean to an S expression? You tell me.
Okay, well, same way we did with the nil. We just put one before it.
So how do I distinguish between an S expression that has a Boolean and the one that doesn't?
If added is equal to flag added, then don't evaluate it like a normal one.
No, but how do I distinguish a normal X expression that has a Boolean without, and then where did the environment go? I was hoping you'd give up because there was no environment. Where's the environment? Okay, so So whenever you go and, it's interesting, whenever you try to muck around with, it's like saying in an int, I'll go put a special value that says it's an invalid value. It doesn't work because all values are valid, okay?
But it's flag say negative or not, I mean, that works.
That works as, as working defined by you, right? Yeah.
I mean, you can put a bit in the high memory order because they're not used, like the first 6 bits of the memory address. I'm just saying, it's still.
You're getting into representation in Java then. Okay. Yeah. Okay, Chris, let's go and have, Chris, let's get your suggestion.
Away from this Boolean thing, can we, like, I don't know if it's going to be right either, but can we store the environment with variables and then use that environment to evaluate them?
So, that's a simple solution. Don't use this function thing. Function is not going to work because it's not a function. Just go and create some encapsulation, which is what we were talking about. And in that encapsulation, go and store the environment and this expression. And whenever we get that data structure, we know it is an unevaluated expression. Okay. So just as we have a lambda object, we have a function object, and this is not a lambda. This is not a function. It is an object, and we'll give it a very descriptive name. We meaning this is the community, and that descriptive name is. Okay. So what we're going to do is, at this point, we're going to do a lazy eval. Okay, lazy eval can do whatever it wants to. It can add a bit in higher order memory. It can go and create a function. But we know that we want to do something beyond just passing that expression E1 and EN, right? And we are not going to muck around with this. So the data structure we're going to create is, and I told you, it's got a very descriptive term for it. It's called a THUNK. Okay. This comes from Algol 68, which was not a functional language, and which had this notion called call by name, and it was implemented using thunks. Okay, so a thunk is nothing else but an encapsulation of an S expression in an environment. That's a straightforward thing we want. Trying to put it into a function object is just not going to work. Okay, and I have a slide later that shows exactly what the differences are, but basically it's not a function object. It is an S expression. Okay, a function object that's got something that takes arguments that are applied to it. It's a much different beast. So let's just call it a thunk. Okay. So it'll be different. It'll be different methods in it. The methods that apply to function don't apply here. So the only thing that is same is the constructor. Okay. And you can construct something that's X and Y, or something that's a point versus something else. So just because the constructor is the same, and the main point is that this is an arbitrary S expression. Okay, it's not a lambda. A function takes a lambda as the first argument. This is an arbitrary S expression. Okay, that's the main difference. But same idea. Okay, I mean similar idea. Okay, so a thunk takes the thing and it stores. It's got a body and a body environment, and it stores these in the variables, in these two variables. And whenever we do thunk factory new instance, we get this thunk with these two data structures. Okay, so after functions, thunks are kind of easy relatively. Okay, because they're less powerful. Okay, so we can define now an eval on thunks. Okay, and what would the eval on thunk do? It will just go and evaluate the body in the stored environment. Okay, so thunk is an S expression. Like any S expression, we'll define an eval method with it. Our eval methods take environments as arguments. A thunk is just going to ignore whatever argument it was passed and use its stored environment. Okay. This is how we do postponed evaluation. Okay. So here's something. Here are the arguments passed. This results in lazy evaluation being called. Okay. Lazy evaluation makes the association, and then the body of the lambda is executed. That tries to do a print x. Okay, x is bound to now a thunk. Okay, rather than expression. So somehow by magic, the eval on the thunk is called, and that goes and says, okay, whatever was there, my body, I'll go and evaluate that, and that's x. I'll evaluate x in the environment in which it was bound, and we get back the result. Okay. Questions? So what triggers the thunk eval? I said by magic it happens. We can just do the same thing we did last time, except our lookup will go and see what it got, whether it's a thunk or not. If it's a thunk, it evaluates it and returns that value. And if it's not a thunk, it just returns the value that was stored in it. Okay. This is take one, by the way. So don't commit this to your memory, as you know, you're going to go much further than this. Okay, but so far so good. Makes sense. Okay, so here's my lookup. I go in. So here's my eval on variable. Actually, it's not the lookup; it's the eval on the variable that we're talking about. That does a lookup, sees what was returned. If it is thunk, then it goes and evaluates it. Otherwise, it goes and returns the return value itself. Okay, so I'm saying in code what I said in words before. Okay, did I get it wrong? Chris, you happy? Okay.
So would we make everything into a thumb whenever we do, whenever we have like a lambda, we make everything into a thumb?
Whenever we call a lambda. Only for lambdas. For now.
So this is editing the lambda.
Yeah, this is just lambda application. Okay?
And then subsequently functions, I guess, as well.
Yeah. Functions will call lambdas. Okay. Okay? Okay. So let's look at this now. When you say let's do everything in thunks, I know there's also a question of to what degree we do thunks. So what's going to happen at this point? Print one arg, if it's called from the top level, nests a non-thunk, okay, the S expression that it got, into a thunk, which is then accessed here, right? Okay, so just trying to recap what we did. Can we get thunks nested in thunks? So let's go and add a level of indirection here. I do a proxy print one arg that just forwards the call to print one arg. It's got lambda ABC and it does func call print arg. I don't know if, by the way, my parens never are probably not matching. Okay, I do func call print one arg ABC, and then I call proxy print one arg with plus one, with the same arguments that I passed in the regular one. So what's going to happen? This is going to nest a non-thunk in a thunk. Okay, so far, I mean, are you agreeing with me here? And this is going to nest a thunk in another thunk. Because that's what a semantics is. We did lazy eval, that went and did another lazy eval. Okay. So that's what's happening, and this is, is there something I have to change now to accommodate this? So what should we do now? I'm going to do at this point when I do print x. Okay, so let's go slowly here. when I go and do print x here, that's going to get a THUNK. It's going to call eval, right, on the THUNK. That THUNK will go and do body.eval environment and return the retval. And that retval will be a it'll be a THUNK. So what should we do? What should we do now? Just go in a loop. Okay? Till you get a non-THUNK. Because whoever's called eval on us needs a value. Okay? And we can make the call, each caller go and see, or we can just do it in the THUNK. Okay? Fine?
I'm sure there's a way you can make that cycle. I'm sure there's some combination of thunks and thunks that cycle forever. I don't know how to do it, but I'm sure you can.
That's like saying, remember eval did 2 evals?
Yeah.
That didn't create a cycle. Why were you so sure then? Because we have remember that, you know, this is being called by here. Now you're saying if in a loop we keep calling, as long as your code that does the call doesn't cycle, you won't get a cycle here either.
Right, but if you isn't there some cycles of loops that in your eval you find yourself? Like if you're, especially in like free variables, free within a nested lambda. Like, couldn't you eval and eventually through that thunk eval find yourself, which is one eval find yourself? Think about it.
You know, okay. By the way, this is, like I said, all from first principles, and I didn't even implement this stuff. Okay, and Andrew was always behind, so I never quite had his code to test it out. But each call is nesting it. As long as the number of calls is finite, the amount of nesting will also be finite. Okay. That's a, you know, you need ultimately to prove anything you need a formal proof, and formal proofs themselves have bugs in them. So, you know, proofs are not absolute guarantee. Okay. So which means you have an infinite number of function calls. And what Robert is saying is that there may be situations where you have finite number of calls but infinite chains here, which, you know, at this point I can't see. And that's Robert's Thanksgiving exercise. Okay. Andrew, you had a question? Okay. So, assuming this all works, and there are no cycles, let's look at side effects. So, can you guys see a problem here? What did I do? I've added in the proxy a set q I3. And I is a global variable. So what issue is this creating? Well, it's not shadowing. It's not declaring another I. It's just manipulating the I after its arguments were passed to it.
We already done in this instance, we already done all that stuff with making sure that functions. So just saying, set queues can be done within lambdas. We've already done all that work to keep it so that if I has been declared outside of it, and you said that I was a part of this function, but we didn't say it was part of the function, so it's going to edit the global I, and then so that it does that, and then it sets it free again for J, and then it's greater than free J. So it's going to edit the global I.
So it's edited the global variable. That's fine.
We're trying to work through it.
Sorry?
But it won't
So, so when we evaluate print x, x refers to I, right? It has to find the value of I. What value of I will it find when we evaluate x here? Sorry? Yeah, so go to the global I. What value is the global I got? It's 3. But had we not postponed evaluation, what value of I would have been used here? Whatever it was before. So we're getting different results. Right? So we're using the same environment, but not the same environment values. And we faced this problem before with functions, and how did we solve it? If we believe this is a problem. This may be a bug or a feature, we don't know. So if assuming this is a bug, how did we solve it in the function? Copy the environment. Okay? So don't go in the THUNK and suddenly we've gone from this one bit flag to a whole copy of an environment. Okay, if we really want to guard against this. Okay, and again, even with eager evaluation and with lazy evaluation, copy is an option. You can just say, you know, you get what you deserve if you have side effects. Okay, or you can say that we will try to do something to prevent them. Okay, so uses value variable in saved environment that have been changed since the THUNK was created, and the expression would have been read in normal mode. Okay, so copy the environment when THUNK is created. That is a solution to this problem. Okay, so that's why we have a deep copy option. So does this mean that lazy evaluation, if we do this heavyweight operation of copying environments, which is, you know, here we're trying to be lazy and we're trying to reduce work, and suddenly we've added work, right? We are copying this environment. So these two things conflict with each other. But assuming that's okay, that copying is less expensive than doing this very heavyweight computation. And just by the way, just to get to it, you know, I'm doing +2, 3 and -2, 3, and it seems silly to do lazy evaluation with that. When I did my Lisp course, it was on something called a mainframe computer, okay? and we had dollar amounts. So I got a $5 amount for each program, for each assignment that I could use. And I did the Tower of Hanoi problem with Lisp, and my $5 ran out before the function returned. Okay, so, and it was correct. So, you know, these things can get expensive, okay? So it's useful, yeah.
If we weren't doing lazy eval, we would still have that same issue with the side effect of the set activity. Like, we would still have that issue, so we would...
No, we don't have the issue when we copy the environment, right? No, this issue's gone away.
If we had, like, granted the way we have it now, we would still have this issue because we don't copy the environment in our current implementation. And so we kind of have to, if we don't want the side effect, then we'll have to copy the environment, whether we do the lazy evaluation or the normal evaluation later, right? Like, we don't want to deal with the side effect because wouldn't that still occur in normal evaluation?
But what we're trying to say is, no. So there are two viewpoints here. The really good viewpoint is that you shouldn't have side effects. When you have side effects, you get what you deserve. The second viewpoint is, I know what I'm doing. I assume regular evaluation. I want those side effects. And you're not allowing me to have, right? So I want the side effects of I being 3, but I do want this I to have been evaluated in the previous environment. That's what my regular evaluation does. So I do want the, so please don't cheat. Don't give me the result that I wouldn't have had otherwise, and let me have side effects. So I have somehow hacked my way into, you know, to solve this problem. And now I'm asking you, if I was willing to copy the environment, and side effects are allowed, can I guarantee can I guarantee the programmer that under side effects, lazy evaluation will be the same as regular evaluation. And the answer must be no, otherwise why would I ask the question, right? Think of the order in which side effects take place in lazy evaluation, and think of the order in which, or order and whether they occur in lazy evaluation, and think of the order in regular evaluation. In regular evaluation, the operations are evaluated left to right. Right? The arguments are evaluated left to right. Yeah.
Because you could have like the y value could be a set q, and then that would never be ran, so that side effect would never occur.
So if the y value had a side effect, it would never occur. Yeah. And even with the x and z values,
Or the z value would happen first, so that side effect would.
so I deliberately put z in the end for that reason. Okay, so I have set q I5 and here, so I put a side effect in x. And normally this would occur first, and this would get evaluated afterwards, right? But what's going to happen? Z is referred to first in the body, so that gets evaluated before set QI occurred, and then X gets evaluated. Okay, so at this point you give up and say, well, I tried, okay, and serves you right for having side effects. Okay, so again, you know, this whole idea of THUNK was invented in the context of ALGOL 68, which is a non-functional language which allows side effects, but it really makes sense. And in ALGOL, you said call by name, okay? You said evaluate lazy. That's like, you know, so that was fine. Here you're saying the person has just not said what they want. Internally, we'll change things. There's an optimization, and suddenly we are getting into trouble. Okay, so this is just, it's just important to understand what lazy evaluation really means. And again, with eager evaluation, if we you know, when we do either, if we copy the environment, if we don't copy the environment, we are not getting the results that we would get with the regular evaluation. Okay, because in regular evaluation, you do left to right, and in eager evaluation, you do them concurrently. Okay, so the copying just made sure that we would get consistent results. Okay, but not the same as regular evaluation. Okay. Okay, so let's become more ambitious now. Okay. So we've gone from lazy logical operations to lazy function calls. Okay. And can we now go back to function? So can we go and now that we have this lazy lambda application, can we do lazy ands and ors with our infrastructure? So can you now go and implement your and to be short circuit? You could. So now you'll get thunks, and you can go and evaluate the first thunk, see what its value is, and depending on that, evaluate the next thunk or not. Right? So we've got this. So more ways to be lazy. Can we do lazy or and in Lisp? So we do less than 5.3 and greater than 5.3. Let's say we do a lambda and. Okay, a lambda and just goes and calls and. So we go and pass to lambda and two arguments. They are not going to get evaluated. Okay, and func call creates thunk, one thunk and another thunk, and the and operator takes its two arguments and evaluates them normally, right? That's what it does. All your binary operations, they take the S expression, they evaluate them. So it can decide to evaluate the first one, and that is a thunk that will evaluate to whatever value is evaluated, and it may or may not evaluate the second argument.
Do our ands not short circuit?
Currently, they don't. They might. So no, your ands will do, but lambda and
Right. Yeah.
lambda and will not. If you pass, yeah. So now it goes all the way. Indirect call also will do the same thing. And the same thing in Java, that if I define a function and pass it to Boolean, yeah.
So if we have our AND short circuit, basically, wouldn't that like make the -5 for okay? So that would be So the first one would be false, and so it would get the AND would see the X is false, and then instantly return.
Yeah, so it won't do the second one.
So
Okay, so actually I posed the question wrongly. The question is, can we do short circuit with indirect calls to and yes, we can. Okay, and your ands are already short circuiting. But I'm saying with this infrastructure, we can sort of make that consistent. And to do this, so not only is the application of lambda operation lazy aware, but the body of an operation is also lazy aware. Okay, your current and also does that, and this THUNK based one also. And then now the body of the basic operation, yeah, that's what it does. Okay, now let's try to find more ways to be lazy. And the question is, just as and is a lazy, and not is lazy, can we think of something else that should be lazy in a predefined operation, in our operation? Huh? Yeah, and or, these Boolean operations, anything else that's more Lisp specific that can be lazy? That will really get us a lot. How about cons and list? Can they be lazy? Okay, so I evaluated 100 elements, and then somebody did a car of the first element and finished. So that's what I've got here. Someone does list one da 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 and does car, and that's my full expression.
So you'll just be looking for the first list or the part of the list that's.
So the only value that'll be printed out is 1, right? Why did I have to go and do all the other evaluations? Similarly with cons. Actually, first with cons, that's the more fundamental operation. And I did a car on that. So why did I have to all the inner conses when all I'm doing is retrieving the first element? And if this is seeming very alien to you, those of you who've used the command line, especially in Unix, if you go and say head -3 of a long file, and you say cat user dash dictionary, and then you pipe that to head -3, you're just printing out the first 2 lines of this big file. Why did you have to do you really have to go and cat the whole file to get the result? No. Okay, and in fact in Unix, the moment those 3 lines are printed out, the head program, you can have an infinite loop. You can have a program that generates an infinite number of lines, and if you go and pipe that to cat to head -2, only the first 2 lines will be taken, and then the program will be terminated. Okay, and there are lazy lists in Java also. Streams, there are lazy streams in Java. And by the way, I just did a search for lazy on Google today, and apparently JavaScript has some lazy stuff going on too. Okay, that was the first hit in fact I got. Okay, so this becomes really interesting, right? That we go in now, so far it was binary. We evaluate or we don't evaluate. Now we are saying we'll evaluate a little bit of the cons. Okay, we'll evaluate enough to get the 1 out, and not more than that. Okay? Any ideas on how to do this? So let's go in. So unnecessary expression evaluations, we didn't have to evaluate this, we didn't have to evaluate this. So unused parts of tuples and lists are not evaluated in lazy tuple and list construction.
These functions need some sort of flag
You love these little flags. You know, I can't tell you how many students have given me code.
I don't see it as a lazy list. I see it as a lazy car. Because like I feel like the car is what's actually making the list be lazy. So
Car will evaluate whatever is given to it. So whatever is given to it better be laziness aware.
how did it know that it's only one person?
Because it's not evaluated until car says get it.
Okay. So cons has to go and say, okay, let's go and let's take something concrete here. Okay. So here's my cons. My cons goes and says e1.eval environment, e2.eval environment, and puts those two things in a new S expression. Okay, this is what our cons did so far. Okay, and the question is, what should we do now? And here's my straw man. I go and say, well, s.LazyEval comma environment. I don't do the new instance. I don't evaluate E1 and E2. I just enclose whatever S I got in a THUNK and return back. Okay, I've got a lazy eval function. I'm trying to hack my way through this thing. So I'm being lazy. So I just go in. S is my application, is this cons E1, E2. And I just go and put myself in put the whole application in a THUNK and return that and say, well, car, you take care of it. Will this work? Yeah.
I'm just trying to think, like, because then you'll also need to change the line of code that basically prints out, like if you do columns 1, 2 or something, you need to change how the map would show it in the console. Because if you don't have something like that, then this just would work.
Yeah, so the question is somebody's using us, right? And it could be a two-string method that's trying to print out, right? The two-string is what's going to print yourself out. And so that would have to somehow handle this, right? But intuitively, why is this wrong? I've got all this space on the right. That means there must be a right solution coming later. Right, in more than one way, I guess. What's fundamentally going wrong here? Chris? So cons, yeah, how does car, what does car do? And the main thing is, has cons done anything that's cons specific here? So we might as well not have cons as an operation. I mean, everybody else will have to do cons somehow because cons didn't do its job. But cons, when it does its job, we don't like it too because it does too much. So, my sort of, the two analogies I use for lazy evaluation is, one is, being a professor in an academic environment, from student point of view, I always joke that the early birds, the Bens of this world who go and do things first, find all the problems and get all the tests, debugged so that the people who do it later don't have to do all this extra work. So the early bird catches the bad worm or whatever, But there's another analogy, which is, when somebody asks me a question, again, I'm lazy. I never give you guys their answer. And people tend to not come to me as often as they go to TAs. Because I always go and try to reduce the problem to a smaller problem. And say, okay, I'll give you this hint, now work on that and come back. So that you can gradually think. So that means that you should make some progress, but not complete progress. So I'm being lazy also. I don't want to give the full solution, right? So I said, go read the notes first. Tell me what you understand, come back to me after that. But that's also your learning also, right? So you need cons to do something, but not everything. So what can it do here? I mean, the answer will be pretty clean when you see it. What does cons do basically? What's fundamentally, yeah?
It would check if either any parameters given to it are atoms in order if they need to be evaluated for the. I'm just thinking.
But what does cons do really? I mean, think of what is the most consy thing here. It combines. It creates a new instance with a head and tail. We've got to do that somehow. right? So I do need that composite factory new instance with 2 elements. And how can I be lazy? Combine 2 thunks. Okay? So, by the way, what's going to go wrong here is const eval will return new thunk, right, in this middle solution. Somebody will call thunk.eval. Thunk.eval will call const evaluator, which will go and call the new thunk, and we just get into a loop. Okay? If we didn't do any work, we'd get into this loop because whoever consumes const's value will get a thunk, we'll call thunk.eval, which will go and call const.eval, which will call which will return a new thunk. Each time it's going to return a new thunk, and we'll just get this memory overflow also and never-ending loop. So what we'll do now, so like recursion also the same idea, but we don't want to just call ourselves with the same parameters. We're going to do some work and then pass the buck to a recursive call, right? So we want to go and do something like this, and we want to return a value with a new instance, and what we return is E1, E2, lazy eval. Okay? So we didn't actually go further. We just did lazy eval of our 2 arguments and returned the value back. Makes 2 thunks. Okay? And let's go and see what's going to happen in this example here. Okay, and please, again, these have been made with only so much thought, so there might be a lot of mistakes here. So I do car cons x cons plus 2, 3. Okay, car is going to go and call the cons evaluator. Okay, cons evaluator, so car is going to do e.eval environment, right? So that's my regular car, by the way. Okay, and that's going to result in these 2 lazy evals occurring. Okay, and car is going to go and return the head of that, which will be, so it's going to get car thunk of x environment, and thunk is going to get 2 thunks. Okay, and it's going to go and return the head, so we're going to return thunk x comma environment. But we made some progress. We got a thunk back. Okay, and now Andrew's question is, we need to print this, right? So the question is, what should toString of thunk do? So the printer will just call toString on the thunk. What should the toString of thunk do? It should go and evaluate itself and then call toString on the evaluated value. Right? That's what we want. So thunk toString will basically do eval null dot toString.
So anything about side effects, naming something toString and having it evaluate sounds like a side effect. Because it's like, you want it to string, I get like that's how you get the string, but like it seems like you've just skirted around the problem. I don't know. Like why isn't it?
So there are 2 questions here. Does this work? And is this good stylistic thing or not? Let's try to figure out whether this works or not. Then we'll try to figure out whether it's stylistically correct or not. So does this work? I mean, that was Andrew's solution. Okay, we evaluate ourselves basically. And is it stylistically correct? It's delegation. It's saying that I'm representing something else. Okay? I'm mask.
Why are we evaluating null at all? Why is it null?
Because eval takes an argument. We have to pass it something. But a thunk just ignores the environment that was passed to it and uses its own environment.
Oh, okay. I thought it was bigger.
So, I mean, the way Andrew said he coded it was that whatever environment it got, it passed it around. But I'm making it very clear that this is going to be ignored. Okay? So basically, thunk is representing somebody else. And that somebody it determines, and it just... Now, if you call toString 2 times or 3 times, each time it will return the same thing. The same X expression. X expressions are immutable. It'll call. We might want to go and store this as in a temporary variable to sort of make sure that we don't evaluate unnecessarily.
If I have a thunk that contains a thunk and we called toString on that, that was the car. The car was a thunk that contains a thunk. So we did toString on that finally, which just evaluated thunk. Is it gonna keep evaluating that, or is it over?
So thunk will keep evaluating till there's non-thunk. And then we'll call toString on a non-thunk. Okay? So by the way, I can't tell you how many discussions Andrew and I have had along these lines. Oh, what's going to happen now? What's going to happen now? Until, you know, this is something that we came up with. Okay. And actually, Andrew was, you know, he was thinking he'd have to do something very strange in the Lisp interpreter, and for every case he had to handle it. So he'd given up, in fact. And so this was actually, in retrospect, it's a simple solution, but it was not that straightforward. Okay. So must change toString of thunk to call toString of evaluate itself, and then you have to go back and say, hey, if you've gone and evaluate, change toString to evaluate, there are a lot of other S expressions operations too. So let's go and change all of them so that it's consistent. That, you know, a thunk is representing the object, and we'll do eval before we do all of this stuff. Okay. So I'm telling you exactly the progression we went through. That okay, let's just go, you know, change all. And this was not what Andrew would first come up with. Okay. Okay, let's do a plus now before this thing. So we're doing plus car cons x da 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 3. Okay, so let plus be the outermost operation. So plus will get first cons is called, then car is called, and plus gets now a thunk. Right? So plus used to not get thunks. Now it gets thunk, but actually we saw that if we make plus thunk aware, we can handle it. Okay, so it'll go in. If plus sees a thunk, it'll go and call the eval on that. So we have to go and change our plus not only to go and let me back off. The and is what we went and made thunk aware. Now the plus also has to be thunk aware. Minus has to be thunk aware. Because they'll call eval, that eval will return back a thunk, and they used to normally just use the eval value directly. Now we've got to go and, if it's a thunk, go and evaluate the value. Okay? Sorry? Yeah, we have to make all of our basic functions thunk aware if you need to do this. Okay? So this was my original plus. It said eval1 equals e1.evalenvironment.getValue, eval2 equals e2.evalenvironment.getValue, return eval1 plus eval2, and now what do? I check if eval1 is a thunk. If it's a thunk, I go and call eval on it. Otherwise, I just go and use eval1, and then I do get value on that. Okay,
Why don't you make the thunk awareness to the superclass?
Okay, we wondered about that. So right now we have no superclass of evaluators. But remember that there are some operations like quote. There was a reason why and cond. There was a reason why we made each operator evaluate its arguments and not evaluate them in the dispatcher. Because cond and quote don't evaluate the arguments. So it would be nice, it will be interesting to see with how we can actually, so try to think about this, okay? So you're more into the implementation than I am. But we certainly are not evaluating all the arguments before calling these operators. Just remember that, Remember, quote argument is not evaluated, and remember, cond also, only certain parts are evaluated. So we'll have to go and make all of these guys THUNK aware. Yeah.
It seems we're just going to be making everything a thumb, like aside from having to thumb everything. Why are you keeping the part where, let's say, it's not a thumb? Because it seems like you write the evaluator in a way that if I type 3, it will turn that 3 first into a thumb and then proceed to go exactly how Lisp normally would, where it evaluates that.
No, that's not true. Sometimes THUNKs will be passed to you, sometimes THUNKs will not be passed to you.
Are there specific instances where
But the thing is that, and so what your solution is that is what again? What to,
basically just turn everything that the user inputs into the thumb and then just treat it as you would having to.
but that's what we did, right? Anytime a function is called, we make a THUNK. That's what we did, and now we have to handle THUNKs. And we want to go and we want to evaluate THUNKs only if necessary. And this is where it comes in. This is where we determine when we get down to the basic operations, that is when we decide whether they're necessary or not. And our regular eval, and before we went and did this partial list stuff, we didn't have to do make these operations THUNK aware. Okay, our lookup was THUNK aware. Our eval of a variable was THUNK aware, and it went and evaluated it. Since we have this partial lists now, and these partial lists can be created without any variables. I can just say const 1, const 2, const 3, const 4, no variables involved. Since we have these lists now that are partially evaluated, our basic operations must become THUNK aware. Okay? Yeah.
So why, I think you went over this like 20 minutes ago, but why is THUNK's get value not aware that every application of get value wants an expression out of it? Like,
actually, we did make get value that way.
right, so why do I need to check it to THUNK? I just say get value and THUNK's going to give me a non-THUNK.
Okay. So that's true. Since we changed get value the way we did,
Yeah.
this will certainly work.
Yeah.
But not all operations will.
Not a val.
Yeah.
Val won't work, but every other one will.
Yes. Quote will. Yes, that's true. Since we changed get value, it will work.
Yeah. But a val doesn't.
Yes. Since we that's a good point. We don't need to. So actually, we get the benefit since we changed the get value there. And like I told you, the get value we just changed automatically because we were changing because we changed toString, we changed get value. That didn't register in my head as a solution to this problem. But you're right. Since we did that, this we don't have to go into that. Yeah. Okay, good point. Okay. So under what Robert said, the only issues are quote and eval and cond. Okay. And now since these operations, since our get values are THUNK aware, and these operations become THUNK aware, I'm going to argue that we don't need to do this. This situation will not arise at all. Our lookup doesn't have to worry about it. We can just doesn't have to evaluate the argument. It can just go and do environment.lookup A. Okay, and whoever needs the value, so we don't need this because anybody who needs the value will go and do the evaluation of the THUNK. We don't have to do it here. Okay. Since we have gone to this new scheme where we are making our structures be lazily evaluated, we don't need to change this, and Andrew's interpreter didn't change. This is my sort of direction I went to show you that there's a partial solution that can work without doing all the other work in cons. So actually this is just fine. Okay, and the basic principle is that anybody who needs the THUNK's value will go and either call get value, which will evaluate itself, or will go and check if it's a THUNK and evaluate the THUNK. Okay. So let's look at quote. What does quote need to do? If it's a THUNK,
If it's
or just return the thunk. Whoever needs the value will go and evaluate it necessary. So consumer of code will evaluate thunk when necessary. So if X is a thunk and you do eval code X, just go and return the thunk, and then if a plus needs it, you'll go and call get value on it and get evaluated.
If I code doesn't evaluate what it's doing, so but it gives an environment, so we try to make it two strings build on. Right?
So it returns whatever was there. If you say code E, it'll return that. If it was a thunk, it'll return the thunk. And let us not evaluate it before we need it. If that may never be needed. So let's go and allow whoever wants that to evaluate it. So that's the basic principle here, that evaluate in the basic operations or toString. Okay. How about eval? There are two eval. Remember, eval was if we first get intermediate value and then go and evaluate that again. So, just like toString, check, or just like yeah. There are two evals here. Which one of them should check for thunk? Okay, Robert's thinking quickly. We just do it on the first one. And think about it intuitively. If we did not do it on the first one, if we did it on the second one, we haven't done any eval specific things. The second one, if it returns, if we get back a thunk and we go and don't do this and do another eval on the thunk, then basically we've done a premature evaluation and the consumer may never need it, and we haven't done any eval specific thing. So we do it on the first one, and if that first one returns a thunk, well, whoever needs the thunk can go and evaluate it. Okay? Okay, guys, this is the one that is the most interesting. This is the one you have to do. So I'm glad you have about 7 minutes to do this. How should my list change? So this is how list worked so far. It created a nested structure ending in the nil atom, and who between the two of you, I don't know who's answered more questions. I'll go for the leftmost one. Andrew?
It would just take, instead of evaluating the heads, it would just make thunks for the heads.
It'll create thunk for the head, but what should it do for the tail? Nathan?
It's the same thing we do as expressions where the head is a thunk and then the tail is a new head with a thunk, with the tail is a new head. So you see the same thing as expressions, only with the thunks. So the tail leads to a new S expression that is a thunk and not thunk.
What thunk of what? I've got S1. With cons, there was, just slow down. With cons, there was 2 items. Expression 1, expression 2. Right? I went and did lazy eval on both of them and created a const structure. You guys are right that we do a lazy eval on the first argument. Tell me, and we better create a new instance of a composite factory dot new instance. What should be the tail of that? Yes, it should be a thunk, but what thunk is it? Rest of the list. So what will happen? Yeah. What's the S expression? It's got the S expression must have E2 and EN, E2 to EN, right? Ah, brilliant. We make a list application on that. Okay. So we return e1.lazyeval and we make list, with the list atom. Okay, so I don't know how to represent that best. It's s.getHead or id atom list and E2 to EN. I shouldn't have this. Yeah, that's right. I shouldn't have this. I don't know what this null is doing here. Yeah? I don't know where it came from.
It's the null
Yeah, but I'm assuming make list just does that. So I don't even know how this nil item got turned into null anyway. Yeah.
How that works, and what happens when you use CDR?
Sorry?
What happens when you use CDR?
Then you'll go and create a thunk.
And then you go to the fund, which has the list as the head, and then it'll evaluate list again. And so then there'll be E2 with the rest of the list with a new list attached.
So you are going to do that every time.
Yeah.
Isn't that beautiful? No? It's great.
It's very elegant and very computationally heavy if you need to transverse that list.
If you want to.
If you need to transverse that list, we're doing this a lot.
So if you're doing
If you need to go from the beginning to if you need to go from 1 to n, you're creating 1 to n lists. I mean,
You're creating one list, you're creating two names.
yes. That's even worse.
so
I mean, it works.
we have to assume a thunk is lightweight here. Yeah.
To make the list, we actually just need to use a expression factory. The head is the list, the tail is the current S dot get.
The tail is an application of the list on the rest of the elements. It's a list application. It's a function call.
Oh yeah, get tail dot get.
This is what the tail is. The tail is list E2 to En. So we've just encapsulated the list operation into that S expression. Is the tail. The tail tells you how to build the tail rather than the tail itself.
Still confused why you don't just do it all at once with a linked list of thunks where you have the head to the tail to the head to the tail. I don't see why that's worse than that.
How long a list did I create?
What? How many times are you cycling through, making lists, evaluating lists every time?
I think the idea is like, say you have like a 100 list and you only get like a 30 element, so then you don't have to deal with.
You would still have to do that.
No, you only have to do the first. I mean, you have to do the back part, which might take longer. But like, say if it's equivalent to making a chunk for the head.
So in the normal case, when all the elements have to be traversed, you're slower, right? When all the elements don't have to be traversed, you didn't go through and iterate through a possibly infinite list also. Okay, so that was the case I was talking about head versus taking the head off the first 3 lines returned by cat or by infinite program. You don't have to run the full infinite program. You can just go and stop where you need. So that's the whole idea, is that you don't create a list that is longer than what you need. You've created a list that is as long as what you need. All you've done is not evaluate the expressions in the list, but your list is too long.
So this only works for head then, because for tail, it would still.
So when you do tail, then you would go and do a get head on it later, right? The tail, if you print it, you'll do a get head on it again. So it'll work in all cases. Okay? You know, again, when you cheat, you kind of figure out what, you understand why things are, you know, when your car breaks down or when some political system breaks down, you understand sort of how things really work, right? So even if you don't like this, you kind of understand better what you did, even if you like that better.
What if you made a version of this where it's like, you've got the head and then a big list of the middle, and then the tail, given that there are more arguments.
Okay, I'm not trying to see what problem you're solving, let me just go further. Oh, sorry, that nil was some thing here, so
You need to create a thunk.
yeah, that's what this is. Yeah, and that thing was some vestigial thing that was, I didn't even see, so that's lazy eval. Yeah, I need to create a thunk. Okay, thunk versus function. So this is perfect timing actually, and perfect question from Andrew too in the beginning. So it looks like they're similar, right? They both have evals in them. They both take the same constructors with the same arguments. But, sorry, basic function doesn't have an eval. You go and actually do the eval on the lambda. And what it has is a get environment and a get lambda. And that's the one you do eval on. And so this is fundamentally different. Thunk environment is a complete environment in which the stored expression is evaluated, right? function environment is the parent of the environment in which the application of stored lambda expression is evaluated. Lambda will go and add to that environment. So they're fundamentally, they're similar and they're different. Okay? So I just wanted you guys to sort of see the difference here. And THUNK eval will never be called. Eval will be called by the application of lambda. Okay, yeah. So I'll go and rephrase this later. Okay, and from your project point of view, there are these settings. So I think I can actually fill up that part in the assignment 4 that says do lazy evaluation. We've covered everything necessary for lazy evaluation. So like I said, this is perfect timing before Thanksgiving. Okay, so enjoy your break, and if you have a lot of time to waste, you have a lot of work from me to do too. Okay, which is all extra credit. It's all discretionary.